Zane Norvill from the School of Engineering and Advanced Technology. The title of his presentation, Removal of Antibiotics in Algal Wastewater Treatment Ponds. Welcome, Zane.
Antibiotics are our go-to drug when we get an infection. But what happens when the antibiotics stop working? You see, with increasing antibiotic use, we're getting more and more antibiotic-resistant infections, or superbugs. Now, much of this problem is from human-human interaction and sanitary environments such as hospitals. But I'm here to tell you about a secondary pathway. You see, after antibiotics are used, they go down the toilet. And if they're not stopped, then they enter the environment, the rivers. And there they can encourage antibiotic resistance. Now, wastewater treatment acts like a policeman, trying to stop the flow of hazardous pollutants to the environment. But they've got a lot of waste to consider, so they don't usually target the antibiotics specifically. So what happens? My research focuses specifically on the antibiotic tetracycline in algae-based wastewater treatment ponds. We grow the algae here instead of in the rivers, and that gets the job done. Most of the time, these are used in rural areas for populations around 1,000 to 2,000 people. But my results are best understood in contrast to activated sludge, the other treatment system there. These are used in cities because they're more compact. And we know from other research that tetracycline does not really get degraded in these systems, but it will get stuck to the sludge in a process known as sorption. This is a good thing. It moves it from a water waste problem to a solid waste problem. But it does let some still get through to the rivers. Now, when I looked at algae ponds, they have quite a big advantage here. Because we want the algae to grow, they need lots of light, so we make them nice and flat. This light allows for photodegradation to occur. And indeed, my research found that this was the most important mechanism of antibiotic removal. And by photodegradation, it is removing the antibiotic and not just sticking it to the sludge. There's a little bit left over in the sludge, but even less gets into the environment, and that's a good thing. Now, I did batch experimental studies in small-scale ponds, both in New Zealand and Spain, measuring the rates of this photodegradation and how much sorption was happening to the sludge. Through these, I was able to put the equations in the computer and relate them to the design of the ponds, the environmental conditions such as the light, and be able to predict the tetracycline removal in algal ponds, perhaps throughout the country. Using these systems, we can predict the removal, understand the issue, improve designs, and hopefully keep our antibiotics working just a little bit longer. Thank you.
Does anyone else listen to these and think, I have done nothing with my life? Judges.
No, I don't think that. But this is fantastic. And Zane, your presentation in Sasakunya's, if we could keep both of them here, Tanya, I think we'd have the river problem sorted. So fantastic explanation and clear explanation of the problem and exactly sort of how that works. So it's obviously quite complex. When I first saw the slide, I thought, well, am I going to be able to follow this? But you explained it incredibly clearly, and the value of what you're doing in that research is very apparent. So really well done.
Thank you, Zane. You've got great passion for your project, and I love the way in which you took us very carefully into the detail of the science, and you're able to relate that to a very real problem, which is the proliferation and the leakage, in a sense, of antibiotics in the environment, and then how that loops back into the problem around superbugs. So I like the way in which you articulated that problem really clearly. And for what is a very complex topic, you did a fantastic job in communicating that. So well done and congratulations.
Thank you very much, Zane Norvill.